Our first device today is a running shoe tester, and that came about because a very good friend of mine started a running shoe company called Newton Shoes. And I don't believe in any hype things. I want to see data. And make a long story short, he doesn't either. He likes data, and he said that the way that running shoes are tested is very, very ancient, antiquated, and he really wants a machine that actually can emulate what the running shoe does to measure the forces and see what's happening. And our task was to develop a machine to do that. And Priam will lead off and tell you all the happy things about it.
And this is working? All right. Well, thank you all for coming. It's nice I would like to introduce the rest of my team. Aaron and Matthew and the other two guys, Focus and Adam, are also on here, but they can't be with us today, but they're here in spirit. Just to start off, this is the overview of the final design that we've come up with. It's a running shoe testing machine, as Professor Slocum just mentioned, and what it really consists of is a 3-axis machine that can get motions in x, y, and theta, and the angular degree of freedom comes from this motor, which is attached to a flywheel, and which is also attached to the shoe that we want to test. The x and y comes from this chaos stage, which is a very neat stage that can have 2 degrees of freedom in x and y directions. And we'll tell you how we came upon this design, what were the little factors involved in the design and building of this machine, and like some results that we have from last semester. Before I start, natural running involves mostly landing on your foot, forefoot mostly, not really your heel. 80% of runners are injured every year, and this number is like tens of millions in the U.S. Runners don't usually hit the ground vertically. They hit it at an angle. But most ASTMs currently test only the vertical axis of running shoes. They really just take a shoe and pound it in and figure out what the energy loss is in a shoe, what the stress strains look like. So this whole problem was like, let's find a way to get some better data about running shoes and how maybe you can help us design better shoes. This is sort of like a neat picture that we got while we were saying this is a Newton running shoe that was given us to one of our the clinician that was helping us, and it basically sort of shows you how people test for the heel side of a running shoe. They just take this big Instron type machine and pound it and get some kind of data out of that. We think we can do a lot better, and so it sort of generated our functional requirements, which were we need to mimic and measure foot kinematics and dynamics during running, from striking of the foot to the ground as well as lift off. We would like to have it have long lifetimes, a high bandwidth, and this gave rise to our mission statement, was to design and construct a biomechanically accurate device for simulating a human foot strike from impact to toe up, and measure different parameters that we'd be interested in, like loads over time, forces, energy return, etc. during a running shoe. So the first thing that we started with was actually looking at high-speed videos of folks running. And this is sort of a typical runner running on a treadmill. And what we did is we used some motion capture to get different points on this running shoe and see how the shoe deformed while it was running. And here you can see sort of a trajectories versus time. This will become important later, but trajectories versus time of this runner. The x, this is linear. This just depends on how fast you're running. This is more interesting. Here you see like the different parts of the shoe moving off the zero position. The heel lifts off, and the midfoot lifts off, and finally the toe at the end. Using this data, we were able to sort of pull out the essential kinematics of running. This is sort of an image of this person running at different time sequences. What we noticed here is that what we like to look at was this angle between the midfoot and the toes. It starts off when a runner slams on the treadmill. It starts off around 180 degrees, 170 degrees. And as soon as he starts, there's a flat phase. As soon as he starts to lift off, the angle slowly decreases to about 140 degrees. And once the entire toe comes off the ground, it starts rising back up again. The speed of running is sort of related to how fast this angle changes. And using all this data, we realized that what we really needed was a 3-degree of freedom machine that can mimic all this. The 3 degrees would be like x, y, and theta. Based on that initial sort of requirement, we went on to figure out a bunch of different strategies. Our first one was, well, let's take a base and start counting the shoe from the bottom, and let's have the base go in all different directions of x, y, and theta. The other strategy that we talked about was actually building a fully functioning human foot, again, x, y, and theta motions. But what we ended up doing, these two machines are, although we could build them, but it would be complicated. It would be easier to split up the degrees of freedom into sort of a 2-degree of freedom base and 1 degree of freedom, or the angular degree of freedom inside the shoe itself. And then the question became, what we would want to use for this base, what we would want to put inside the shoe, and how we would sort of control the whole thing. So again, we came up with a number of different ways to do each one of those individual parts. One was creating a phantom foot that would actually go inside the shoe. What the phantom foot must do is replicate the stiffnesses of your feet while you're running. There's different strategies, again, involved in doing that. One way to do it was just to build a system that had a bunch of links, that captured the essential motions of your foot while you're running. The other way to do it was to actually create the shell, or this internal end shell, and then cover it with some kind of silicone or epoxy that would capture the right stiffness as well. For the base itself, to capture the 2 degrees of freedom at the bottom, we could use cams. We could use something like a 4-bar linkage to generate the right kinds of motions. We could use a 2-degree of freedom stage. And at the end, we would have to instrument this entire thing, put in force sensors and displacement sensors in the shoe itself to measure and see if we can capture the right motions. And this is what our final sort of MATLAB simulation of this all looks like. You have a shoe or multiple shoes mounted on like a flywheel with a moving base, and this moving base would strike the shoe, so that it would look like the person is running. The trajectories for all of these were determined using the data that we had from before. The x and y motions need to be decoupled, so that sets limits on what we can do. And here's a little graph of sort of a point on the space, how it would move in time, just go back and forth. And we would mount sensors both on the base and on the shoe itself. So Matt will talk about the detailed design.
All right, thanks, Priam. I'll talk a little bit about the different modules that went into our final machine. So different modules are the phantom foot itself, which is shown right here. Phantom foot is bolted to the rotary stage right here, which spins around in a theta degree of freedom. This is connected in turn to this chaos stage here, which as Priam mentioned moves in the x and the y degrees of freedom. At the same time, we have sensors that are placed, force and pressure sensors placed within the shoe here that measures real-time impact data. So what this design allows us to do is to basically have the ground providing all the forces, and the shoe can be passive. The shoe doesn't have to have any kind of actuators in it. So the question then became, how do we design this shoe so that it accurately represents an actual like human tissue and bones? So the phantom foot, we first talked to an orthopedic surgeon named Dr. Thomas Borderer, and we also did quite a bit of research into what exactly the foot is doing during the impact, during running. We found that it's actually extremely complicated. During our 1-semester class, we needed to find the best way to simplify basically the construction of the foot with the machine that was easy to machine, but at the same time gave us an accurate representation. So the device that we eventually came up with was simplified into basically combining the tibia and fibula into one piece, one rigid piece. Coming off of that is a flexure, which represents the metatarsals. Coming off of that is a smaller, more flexible piece of metal that represents the phalanges. Basically, by prescribing what type of metal and the exact thickness of the piece of metal that we use in here, we can prescribe what stiffness that the structure will have in order to represent the stiffnesses of the muscles and the joints within the foot. This is an example of an equation that we use in that calculation. So in order to make the phantom foot, first what we did is just machined out of aluminum and steel the pieces of metal, bolted them together, and this formed the skeleton. Then we took one of our feet, put it in clay, took it out, we inserted the skeleton and poured around that this gel-like substance which was similar to which basically simulated human tissue. Then we took that out and put a shoe around it. What this very versatile module enabled us to put different types of shoes. This one is the Newton, for example. We could put all different kinds of shoes on there, left or right. We could scale this to accommodate different shoe sizes. And this entire module could just bolt onto our flywheel. So we could have, it's just a very versatile module. In the future, what we would like to do is split up the metatarsals into maybe two joints, like a 2 and a 3, to reproduce the kinematics more accurately. Now I'll talk a little bit about the rotary stage itself. So the rotary stage consists of the motor, which provides torque to the flywheel. Now the flywheel needs to have relatively high angular momentum so that with each impact on the shoe, it doesn't slow down too much. To the flywheel are bolted the phantom feet, and this entire rotary stage is bolted through this MK stock to a very rigid granite table to reduce vibrations. Now in selecting the motor for the rotary stage, there are 4 primary variables that we considered: the torque, the speed, the power, and the radial load. Now in order to find the torque, what we looked at is roughly what are the shear forces that a runner experiences while they're running. And it was referred to as the anteroposterior force, a graph of which is shown here. By taking the peak anteroposterior force and multiplying that by the radius of the flywheel, we can figure out what kind of torque that our motor is going to need to produce. Now the speed, we want that to correspond roughly the running speed of a marathon runner, which came out to be approximately 80 RPMs. Multiplying the torque and speed gave us the power requirements for the motor. Now for the radial load on the motor needs to withstand forces against the shaft like that, which sometimes it's not designed to. Basically, these forces represent the vertical impact forces that the shoe experiences while running. Taking these 4 variables, we selected a motor which satisfied the requirements. Now you can see these numbers are actually pretty low. Like the normal force right here of 230 pounds. We'll come to think of it like a 200-pound runner is actually going to produce a lot more than 200 pounds, maybe even up to 400 pounds while they're running. The reason why we selected this motor was because we wanted to match the capabilities of the chaos stage. For our proof of concept prototype, the chaos stage that we had actually wasn't powerful enough to exactly duplicate the force requirements we need. So that's why we selected this motor that would match its capabilities. In future iterations, future prototypes, we use more powerful chaos stage, more powerful motor to more accurately reproduce the running kinematics.
All right, so I'm going to talk about the base stage and then also the instrumentation for the shoe. This is a representation of the chaos stage. So this is a magnetic base with 2 individual stage cars in the red that are moved independently. And then on top of each of those is a rail that sits on top of the base that hits the shoe itself. So by controlling these 2 stages individually, we can create motions in the X direction as well as in the Y direction. When they move together, it's along the X. When they move against each other, it's in the Y direction. This is an example of our control panel that we used for it, which I'll get to in the next overall scheme of how we control the device. It was limited in terms of performance from an actual runner, and from this plot here of what our desired motion is to our actual motion, it does not achieve it due to some limits that I'll show in the next slide. Here's our overall control structure. So we give the rotary theta motor a constant velocity or angular speed that we use an encoder to read the position of. And this is our overall control scheme. So we take this angle, and based on that angle, we know X and Y position desired, and we transform that into those two individual cars for where they should be at any given time. We send that control signal to amplifiers that actually use closed loop control to control this chaos stage. And one limit for us was this analog set point signal. With a different control scheme or a different product instead of DSpace, something that provides a digital signal to these amplifiers as opposed to an analog, we get better resolution and we'd be able to more closely match our desired set points as opposed to what you saw on the last slide with poor tracking. For our sensors, we need to measure the displacement as well as force on the shoe in the insole. So we measured the displacement with Hall effect sensors using a magnet and then a Hall effect sensor. The signal coming out of the Hall effect sensor depends on the magnetic field in the area, and through that calibration we came to this equation that is able to measure through the thickness of the shoe without any connecting parts over a long range. For the force, we use these TechScan Flexiforce sensors that are very thin and then measure the force over this contact area. These are cheap and fairly easy to locate, as shown on the bottom of an insole. We use these 4 points, and in further iterations we use more points. Another TechScan device uses an entire insole with over 1,000 sensors located throughout it, but for our proof of concept that wasn't entirely necessary. All the instrumentation is provided within the shoe, so the Hall effect and Flexiforce sensors come out of these wires, whereas the magnets are located in the actuated base. However, since it's rotating around, we need to provide a data connection to it, so we use this slip ring with a USB connection essentially, and an instrumentation connection on the rotating flywheel. So an actual video of how it's moving. You'll notice some slip between the actuated base and the shoe hitting it, which is due to poor tracking, which would be improved in further iteration. So some of the acquired data to show that how these sensors are working, and it is acquiring data. These are two signals of the displacements, and you can see that at different points in the shoe you're achieving different displacements, so there is some relative motion between the two. And then as well as the force, it's impacting different points in time. So by combining those, you can look at the energy absorbed and the energy returned from your shoe. Due to the tracking of our stage, these forces are not terribly high, and with improving that, we improve the actual forces of the shoe, or of the simulation. This summarizes what we set out to do and what we achieved with our testing mechanism. Some of the things we'd like to improve on are the phantom foot of actually more closely simulating the desired stiffness, as well as the trajectory following of our chaos stage, which would easily be done with a different control hardware or architecture, as well as different force sensors in the shoe. Also like to note that out of this, we have a patent pending on our device and testing scheme. We'd like to acknowledge these people for their help and assistance in doing this project. With that, are there any questions regarding this? Yes.
Was there any discussion early on around looking at out-of-plane motions?
Yeah, we did actually talk a lot about sort of getting the sort of pronation, supination part of running. For our first iteration, we decided to just do building like that'd be like a full 5-axis machine. But building something like that, we just decided to go with something that's simpler, more easier to build. But you're right. We would have to instrument something on the base itself that really strikes the foot at different angles, as well as something that sort of hits it flat.
What shoe should I buy?
We don't know yet. We need. They'll probably ask us after the patent. The questions. Yes.
Yeah, two cents about this compares to what the athletic shoe industry does to test their shoes.
So
you probably looked into this a bit.
That's actually very interesting. So if we go back to something here, so the most like the standard tests or the ASTM tests are just you take something like an instrument machine and you just pound the heel because that's sort of like the only way to not destructively test a shoe. So take something and just measure the cushioning during the heel. But if you notice how people run, there's a lot of impact on the toes and on the midfoot as well. So this is another test that's sort of done in the industry to characterize something like that. But again, if you want to do that, it's a little bit of a self-destructive. It's a destructive test, and sort of slamming it this way. Like, how well does that actually represent the sort of the deformations that your foot undergoes, the deformation that the shoe undergoes while you're running? It's not. Well, I mean, we thought that like building something that's like actually more like a foot would work better. So these two tests, one for the heel, and one for the toe, is sort of what generally is done in the industry. The other thing that we've seen also is that people just take a shoe and kind of bend it to sort of do more of a flexural kind of test. That again is like how well does that? That doesn't really capture running very well, in our opinion. Actually, I don't think we went through the entire video. If you guys want to see it again, I think it's very exciting. But if you have any other questions, I can answer now.
Remember, the interesting test on running is what Danny says.
But what Danny says is interesting. Take your shoes off and go run barefoot. And if you try running barefoot the way you would run in like normal running shoes, you'll kill yourself. It's terrible. And the humans seem to be evolved without shoes. So that's kind of a good hint. Anyway, that's this guy's shtick, is that you should be more on the toes. And he designs his shoes to encourage that. Of course, you can have anyone's shoes. It's just how you train to run. So that's one of the things we're ultimately in the research we'll be trying to do is look at when we emulate toe running versus midfoot versus heel striking, what are the forces involved, and get some real actual data then for very high cycle